Welcome back. So if you remember my lecture that I had on the monotone framework and flow-sensitive intra-procedural analysis, then you will also remember that I talked about the relationship of the MOP and MFP solution. The MOP solution, like I explained, it's the sort of optimal non-solution that you can think of, right? So unfortunately, it's not a solution because it's not computable. But if we were able to compute it, it would give us the optimal, maximally precise result. But normally we have to approximate this, right, to the MFP solution. And I explained to you that in the MFP solution, we are merging more frequently, right? So in the MOP solution, we are only merging across all paths at the very end of the computation, but because that's not tractable, in the MFP solution, we are basically merging whenever we hit a control flow merge point. And this gives us some approximation in the very general case, but you do get the guarantee that the MFP solution is an over approximation of the MOP solution. So, you know, it might not be precise, but it will definitely be sound. What I also discussed was that you can have analysis problems that are distributive. And in the distributive case, it doesn't matter when you merge. You can merge earlier or later. That doesn't matter because the merge operator, by definition of distributivity, the flow functions, they distribute over the merge operator, right? So flow function application can be done at any time between merge operations and the other way around. You're guaranteed to get the same result. And this also means that for a distributive problem, the MOP solution is the MFP solution. So you do not lose any precision, which is really nice. Unfortunately, precise pointer analysis is not distributive. So that's a large disappointment, right? So we cannot come up with a points to analysis algorithm that will be 100% precise for any program. You will always have to cut some corners. And I will show you an example illustrating that that is the case. And in some of the upcoming lectures in this course, and in particular also in DECA II, we will be talking about algorithms that actually solve nonetheless this pointer analysis problem to a very large extent. So they do still have to approximate because, you know, I will just show you it cannot be done otherwise. But they approximate in such a fashion that you really lose only precision in some corner cases, let's say, that are not very prevalent in practice. So I was talking about precise pointer analysis. You can have imprecise representations, like what I'm showing you here, which is in the literature also called the so-called compact representation. That is distributive. So here we have a representation that looks like this. So whenever two variables are aliased, like here, A and X, or B and A, we simply put them into a set. That's somewhat similar to what I showed you earlier with these access paths, right? So this is a bit imprecise, right? Because now we merge this here, and now this is telling us X and A and B, they alias, right? Although in the right-hand side, only A and B alias, and on the left-hand side, only X and A alias. So in particular, there's no path to the program along which B and X alias, right? That's just not possible. But this set tells us that that could be the case. Okay, so in that sense, this is imprecise, but it is distributive. Okay, I won't prove that it is distributive here, but it's basically a set-based representation. And if you use set union as a merge operator, that's always distributive. That's very trivial to show. So the compact representation that I showed you, it represents points to relationships in an undirected way, right? So we were using sets to represent these pointer relationships. And that is very similar to Stensgaard's flow and sensitive equality-based analysis that I showed you earlier, which in Spark can be represented by these bidirectional arrows. It is distributive because we're talking about pure set operations, but it's imprecise because in the example x and b can never actually alias. Okay. Now I'm going to show you the same example again with a different representation, which in the literature is frequently called the graph representation. And here we have a directed representation. Okay, so this is saying A has been assigned X, but not the other way around. This is saying B has been assigned A, and so on. And now, importantly, when we merge this, we don't just merge across everything like we did earlier, right? We're merging the individual mappings, basically, right? So we're merging them together, and we still have both of the original relationships that you saw here, right? And this would not indicate that B and X may alias, right? So they're being kept separate. So the graph representation stores individual points to edges. That's rather similar to what you saw in the pointer assignment graph in Spark. It's a directed representation. It avoids the introduction of spurious information at merge points, like I just showed you. But unfortunately, it's also more expensive to compute because the flow sets become larger, right? So you can imagine we have a larger abstract domain, right? In the compact representation, our domain is a set of variables. And here we have a set of pairs of variables, basically, right? Or a set of mappings. When does that become important? Let's take a look at this kind of program here. So we have an if branch and an else branch with different kinds of assignments. And in particular, we have some aliasing introduced for this variable x, and then we are updating some field of x, okay? And here I'm showing the very same as a control flow graph. Same program. We have an if then else, and the one block we do this, and the other block we do that. And then here we have this assignment to this field of x, okay? And now we're assuming we're using the graph-based representation because, like I said, the graph-based representation is more precise, but my point of this slide and the following ones is that I want to show you that unfortunately with such a precise representation, this is not a distributive problem any longer. Okay, let's take a look at that. So here we get these mappings out of the left-hand side. That's trivial. The same for the right-hand side. And now let's assume that in the style of the MFP framework, the monotone framework, we are merging these two sets here first, and then we are applying the flow function for that statement down here. By merging, we simply do a set union over whatever we have here, so we get this combined information. So far, so good. This has now been merged together, right? So this is now the single input set that we get for the flow function of this statement here. And now we are computing the relationships that can come out of this assignment. And you will see that there are actually quite a few. There are still the original relationships that we had here, but there are more. So in particular, x.n now definitely can point to y, right? That's this relationship here. But because a and x may have been aliased, a.n can now also point to y, right? So we also have this relationship, the same here and here and here and here. I don't want to go through all of these, but what I want to talk about is this relationship here, because that's, so to say, a false positive. That's actually something we don't want. Why? Let's take a look at that. So this is saying that a.n could have been assigned the value of q. But look at the program and see whether that can actually happen. what do you see? You might see that, well, because here on the left-hand side we have a dot n, and a is being assigned only here on the left-hand side of the branch, this sort of implies that we must have come along this branch, right? But q on the right-hand side can only occur when we also take the right-hand side branch, right? So this here, in this case, we are being assigned b, but here we are being assigned q. So what this means is that these assignments, so these two assignments, they correlate with one another, right? And these two assignments, they also correlate with one another. You cannot have a program execution where you have this assignment to x, but that assignment to y, or this assignment to x, but that assignment to y. That cannot exist. Nonetheless, by this merge, we are merging the information of both of these branches together, forgetting about this correlation, right? And this gives us, in this case, really an imprecise solution, so to say, of this flow function, right? So this is a pointer relationship that can never occur at runtime, but nonetheless, because we merge here first and then apply the flow function, we get an approximative solution, because basically our merging was a bit over-eager, right? So it merged at a point in time where ideally, if we had had a choice, which we don't really have, because the MOP solution is uncomputable, but if we had had a choice, we would have kept these apart, and then maybe we might have gotten a more precise solution. And in fact, that's the case. So let me show you the situation where we pretend, we would be doing exactly that. So here, let's assume we are implementing a program analysis algorithm as follows. So here we are keeping these results apart, and we first apply the flow function, but individually to this value and to this value, okay? And then we merge later. Let's see what happens here. So on the left-hand side, using this information here, we would get these results. On the right-hand side, we would get these results. And nowhere do you see this here, okay? There's on neither side do you see a.n is assigned the value of q, which cannot be the case, right? Because the point is exactly we are not conflating these two sides now. We're keeping them separate. But if you now were to merge, if we now take a union of these two, well, then obviously in the union, you also don't see this result, right? So this is really more precise. And it has become more precise because we have merged later, okay? And that's exactly a proof, or a counterexample, you could say, illustrating that pointer analysis is not distributive, because it had been distributive, you would have had the guarantee that the results are identical. And clearly here they are not, right? The result where you merge earlier, it's more approximative. So merging first gives you different results than merging later. Therefore, the flow functions, they are not distributive, right? So they're still sound. That's fine. You get an approximate answer if you merge earlier, but they're not distributive. And in fact, that's something I won't talk about in much detail here. It's something you can also read up in the literature if you're interested. The particular problem that I talked about here, flow sensitive and field sensitive alias analysis, or actually any flow and field sensitive analysis, is not even decidable. So it's not just not distributive, you actually cannot precisely compute it at all, right? So you can never actually have that. Thus, you must approximate. That's something that you cannot avoid. But like I said, by merging first or merging earlier, you still get a sound, nonetheless, maybe imprecise approximation. And that's generally true for monotone frameworks, right? So this fact here, that you get a sound answer, we showed that earlier, that you're guaranteed the fact that MFP is a superset, so to say, of MOP. So your answer will always be sound. Okay, just to recap from this week's lecture, so we talked about certain points to analysis that can be used also as alias analysis, so to answer alias analysis queries. And that has some advantages. For instance, you can just reuse Soot's points to analysis using Spark that was used to compute the call graph, but then you can also reuse it to answer alias analysis queries. But I also explained to you that that has some limitations. In particular, you should not be choosing VTA then. We also discussed that must alias analysis that only makes sense in a flow-sensitive setting. And we also discussed the notion of so-called strong updates, which replace the abstract information associated with a memory location. And we also discussed that this is only sound if you have positive must alias information on the aliased variables. Then I explained to you that flow-sensitive and field-sensitive points to analysis is not distributive, and therefore it must be approximated. That's all I wanted to tell you about pointer analysis. And during the next few lectures, we will then be talking more about inter-procedural analysis and the different kinds of frameworks that are being used there. I will talk to you then. Bye-bye.